without further ado, we'll get started. Thank you everyone for joining us and excited to share with you today. So this is a subject that I care deeply about. I've been involved with Passive House for a very long time now, well over a decade. The first one I worked on was supposed to be Bryan Cranston's house. He ended up doing lead platinum instead of Passive House because this was back in the PHPP V2 days. Um, and it's a standard that I care a lot about. So I speak with all of this with a lot of love for it and having been involved with many passive houses. So today I just want to offer a perspective that I've come to throughout my work over the last couple decades on lots and lots of these types of buildings on how maybe we can level up passive house a bit by using good materials as a fundamental element of that work. And as you can see here, I'm broadcasting from my house here in Tucson, Arizona. Thank you for joining for wherever you're joining from, and excited to share this message with you. So, brief introduction to myself. I was in a pre-med program at UCLA, got really concerned about the future of our planet by reading a book called The Future of Life by E.O. Wilson. Became very involved with the climate activism movement, joined this thing called the California Student Sustainability Coalition, got pulled into some pretty massive stuff around that. Then had a time, uh, where I decided I needed to dig into the data and research and learn how to do research better. So I went and got a Master of Environmental Science and Management, which was paired with a green MBA. And I figured that understanding, being in a capitalist society, understanding how business works would be an important element of making this work real. And all of that led me to become a building scientist. I started by getting a Building Performance Institute building analyst, a BPI BA if you're familiar, then got certified passive house tradesperson and got involved with all those different things. And I've bounced back and forth between doing utility program management, being a builder, so kind of just being in the trenches, understanding the applied reality of how building science works out in the field. You could say my career has been an attempt to understand high performance, good building from as many angles as possible. And now I'm honored to serve as the chief building nerd at a company that we call Nopal. And you can find information about us on our website, Instagram, and you can email me if you have questions. Oh, and I like to say I've had a pretty awesome career. I've really enjoyed it. And the way we talk about these things, instead of green building, high performance building, whatever it might be, we talk about this as good building. So the intent of this presentation today, right? We want to share a philosophy and process that we've come to after a lot of experience trying to do Passive House and other similar standards. We want to try to provide some helpful tools and examples from our work. And we want to suggest how we can discuss some tough topics, tough for people to understand, tough for people to accept, et cetera, et cetera. It's something that we've become hopefully pretty decent at over the years of talking these things, especially with clients, with homeowners and developers that we end up working for. It's important to communicate these things in ways that they understand that don't make them feel defensive and all those things. So our work is inspired by Passive House. That, as I said, that's been a core part of the inspiration of my work. Living Building Challenge is something I've been involved with for a very long time now as well, especially the materials pedal. We care deeply about health in buildings, maybe above all else. That's what we focus on. And a love for humanity and nature. We want our work to help heal our planet, help heal humans, help create better family environments, better athletic performance through having healthy air, healthy water, these kind of things. And this rendering below you see is a project that we're going to be working on as part of our applied research as a development we're going to build ourselves to help try to achieve some of our goals, right? So fundamentally, our goals are about creating joy through low carbon construction. We want our work to be very low impact, but to create a lot of joy, and not just for the client, but for us, for the trades who do the work. Like, let's build a community around these types of projects, right? They can become a call for a more exciting, better future instead of using fear to motivate, right? We can use joy and excitement. And then what's really important is using science to optimize both mental and physical health. The mental health elements are usually biophilic design, that kind of stuff. Physical elements are, like I mentioned, clean air, clean water, good acoustical quality, these kind of things to help you relax and recover. So what do? We do building science consulting work all over the Western United States. We do development as applied research in Arizona. We're based in Phoenix and Tucson. I'm in Tucson. My business partners are in Phoenix. We do design and build work. We call it good design, good building for residential projects in Arizona. And then one of the things we really have focused on is trying to take all of our experience and create an open source educational platform online. Our research is always rooted in the field. In the last couple decades of doing this work, I found a lot of building science is really detached from the realities that occur in the field while trying to do high performance good buildings. So our work is always rooted in understanding what occurs in the field and how that can inform the design work we do. We also do a lot of classroom kind of education. This is myself and my business partner, Austin, with a wonderful woman named Beth, talking at the American Society for Interior Designers, talking about how finish selection and all that can really help with health in a human and planetary sense. We have YouTube, Instagram, where we post videos and stuff to educate people about the work that we're doing. And then we have a website that we're developing to try to be, I would say, the simplest and the most elegant sense way to explain this to people who are new to these things, trying to explain it from a different perspective than we've seen before. So one of those examples is talking about performance layers in buildings as base layers. For a long time, I used this jacket analogy, different jackets. But what I realized over time is jackets are associated with aesthetic elements of people's like wardrobe, right? People care what their jacket looks like. So when I'm using that analogy, people are assuming I'm talking about cladding and interior finish and stuff like that, that really I'm not even talking about. I don't really usually care all that much about most of those details as long as they're not screwing up my performance layers that I'm specifying. The aesthetics I'm pretty agnostic to. So a base layer approach is a really interesting way because it makes people realize, oh, it's just the stuff kind of underneath all the layers that I care about. It's the other stuff, right? So this base layer approach has been a way to effective way to communicate these things, right? Um, so yeah, here's a cute little drawing we did to show this and kind of communicate this on the website. And these base layers are asked to do a lot of things, right? And the main point I want to make is that when we're thinking about a base layer system, we really come to the passive house formula. I didn't put, good windows on this, but the other four ones, right? We have thermally broken framing. This is a system that we're designing to make it so we can build buildings faster for a lot less money, skip the hassles of exterior insulation, but still deliver passive house levels of performance. That's the goals we have with this. We have our control layers, right? That's another one, make it airtight and hopefully, be vapor permeable. There's insulation layers, right? We tend to use a mix of wool and wood fiber for a balance of, carbon impact, moisture mitigation, thermal mass, all these other things that we'll get into later in this presentation. And then our mechanical systems, the lungs of the home, right? And as you can tell, that's basically four of the five main passive house principles. If we added windows, we'd have all five. So another thing we talk about a lot is this thing I call the efficiency trap. It's very much something that occurred in my own career, and I'll add some details about that as we go through this. So at some point, let's say like the 70s, oil embargo stuff, right? We were like, we need we need better buildings, and these better buildings, they should be comfortable, healthy, affordable, low carbon, durable, socially equitable, all these good things, right? And then it became this moment of like, okay, great idea, but good needs to be quantified and green's too political. So let's talk all about all of this stuff as energy efficiency. That'll be our proxy for all this other stuff. Cool, solid plan. We can sell that to the American market, right? Like, let's do energy efficiency. And obviously, efficiency matters a ton. It's a very important thing. But it became a proxy for so many things that were just assumed to happen along with energy efficiency, optimized health, optimized carbon impact, et cetera, which the data shows isn't necessarily the case, right? Sometimes it is, sometimes it isn't. So we got really obsessed with efficiency and tried to maximize efficiency and show that we delivered efficiency efficiently, you know. And there's kind of a voice that starts going, but that's not really the goal, right? Like there's other stuff we're trying to do. And then efficiency really catches on. There's all kinds of certifications for systems for efficiency. And then Passive House comes out. And I would argue it got as close to perfecting efficiency as any system ever can. And there was this kind of feeling of, oh, wow, well, this standard, right? The world's saved. And then there was a moment of, oh, snap, it turns out efficiency delivered with bad materials ain't going to save the day, right? Like a passive house built with high carbon impact unhealthy materials is not necessarily going to turn out to have the outcomes that we all hope our buildings to have, right? So we come back to this question of what about all the original goals of health, comfort, durability, embodied carbon, social justice? How can we achieve those? And the conclusion we've come to is should we consider a materials first perspective, right? Like put the materials as the materiality of the building as the first thing we think about. So we've come to summarize that as the ingredients create the results. This is a kind of fun way to show it and very simple. This is my business partner's older kid when they were building this backyard shed we were doing as part of our applied research. And this is insulation your children can literally play with, rub on their faces, and have it be totally safe. The wood fiber insulation that you're seeing blown below, the guy's wearing a dust mask to install it, right? Like that's the whole getup you need. If you're having to dress up like you work for the CDC during an outbreak to install insulation, it might not be the greatest thing to have in your house, right? Like it's something we should probably question. And one of the things that I want to emphasize is both these could be passive houses, but they'd be fundamentally different buildings in the way that I think about it if one is based on spray foam and the other is based on healthy natural ingredients. So a way I have summarized that is design cannot turn bad products into good buildings because the design occurs way downstream of the where the impacts start with various products we use, right? Like this is a great image, I think, borrowing from Havelock Wool, talking about where their fibers come from versus fiberglass fibers coming from, right? Like think through that entire product life cycle of happy sheep in New Zealand versus, huge factories and stuff producing fiberglass, right? Like you can't remove that impact that's already built into those products, no matter how efficient your building becomes, right? You can mitigate them, you can reduce them, but you're always starting from a higher impact start point when you've used materials that have, high impacts built into them. So I also would say efficiency cannot turn bad products into good buildings. So how do we as a company, what's our process, right? Like that's our philosophy that I just shared. And now what is our process? How do we create good buildings, right? Like what do we go through? So the first step is curating ingredients. And over the last 2 decades of work across hundreds of buildings, we've come up with this idea of the 5 factors of good building. I want to emphasize it is not a certification system. Um, it's more of a framework for product specification, right? So like when we're thinking about the ingredients creating the results, we're got to ask, okay, well then how do we, in as quantifiable way as possible, select the ingredients and explain to clients and whatever, why are we using this product versus this other product? I read all this stuff on Green Building Advisor that spray foam's great or whatever it is, right? You guys are saying it's terrible. Like show me the data, right? So how do we talk about these things? And I'm not saying it's perfect by any means, but we've found that this is a really effective framework for having these conversations with a lot of different people. So 5 factors are comfort and health, efficiency and renewables, durability and resiliency, social equity and embodied injustice, and life cycle carbon impact. And throughout the rest of the slides in this presentation, I'll get into more detail about what all of those are and how those inform our design decisions and product specifications. But first, just give it a little example of what this can look like, right? So um, the first step, and this is one that I think is often missed, is that a chef friend of mine said this to me once, is even the best recipes can be ruined by one rotten ingredient, right? And with that philosophy, that concept in mind, we start our projects with a do not use list. It's a list of materials that we have come to by working with whoever's on the project team, from architects, engineers, builders, homeowners, whoever it is, saying these products are not going to be part of this project no matter what. We're agreeing to that up front, right? Like those are banned. Don't even bring them up, right? Um, and then from there, we can start putting together an aspirational list of products that we want to use, of materials we want this building to be made out of. So, one of the ways to visualize this 5 factors analysis is a score out of 50 points. And spray foam insulation, in this case, closed cell spray foam and stud bays, gets 16 out of 50 points. It can do a decent job for delivering efficiency, right? The R value definitely doesn't translate to real world performance as well as you'd think, because foam's very low density. We'll get into that in more detail in a little bit here, but I'll give it some credit for efficiency, but for comfort and health, for durability, for embodied injustice, which is a term we'll get into more, but it's about social justice and product life cycles, and life cycle carbon impact, spray foam tends to be one of the worst, right? So you compare that to say, and give that a big red thumbs down. Then we compare that to say wool insulation and stud bays, right? Very good durability, great embodied injustice characteristics in that there's very little, very low life cycle carbon impact or carbon storing. There's amazing comfort and health properties of wool in particular, and great efficiency. And I've just noticed I put 2 eyes in efficiency, so I guess there's extra in this efficiency. So yeah, big green thumbs up, right? And just this is a visualization that we've used to explain to people in a really simple format why we're choosing one thing versus another. And it just kind of makes it easy to have that conversation. So if you haven't ever seen it before, this is what a blown wool insulation looks like. We have a service cavity built in front of that for plumbing, electrical, and all that. We were originally going to cover it with an air tightness membrane, but in Arizona, one of the big problems we have is interior air being too dry. And wool has an amazing ability to absorb a lot of water vapor when there's excess humidity from cooking, showering, or whatever, and then help re-release that humidity back into the environment. Excuse me, wool can also irreversibly bond formaldehyde and a few other chemicals. So leaving it exposed also provides some degree of air filtration benefit. And most of our insulation performance in this building in particular is on the exterior side, which we'll get into in a second. So this is the designing for comfort element, right? Where exactly does the insulation go? Like asking more questions than just R value. We found, especially in our climate, where there's massive diurnal temperature swings, it can be like, 30 degrees in the morning and 80 degrees in the afternoon. With these kind of huge temperature swings, R value tends to be a very poor prediction of real world performance. A much more accurate way to predict real world performance when we dig deeper into like how thermal transfer actually occurs is what's called thermal diffusivity. And you can think of it as simply as heat conducted through a material over the heat stored divided by the heat stored in that material, right? So basically wood works out to be one of the best balances of these characteristics because wool has what's called a high specific heat capacity, right? So wood fiber insulation I know I've been saying wool and wood, so this is probably getting mixed up here a little bit. Wood, like the stuff that comes from trees, has a very high specific heat capacity. It takes a lot of energy to change the temperature of wood fibers themselves, right? Whereas foam fibers have very low specific heat capacity and don't take much energy to change their temperature, like of the fiber itself, right? And then you multiply specific heat capacity by density to get that heat stored number in thermal diffusivity. So some things like wood have extremely good thermal diffusivity properties, as you can see circled here. Other things like foam have pretty mediocre. And then things like mineral wool actually have very poor thermal diffusivity properties. If you think about how quickly a rock heats up in the sun, and then think of mineral wool as like a low density rock, then it doesn't conduct that much heat in the sense of its R value, right? But it also doesn't store much heat. So a lot of heat energy actually warms up the material itself, and then that heat can conduct into layers below and warm things up more than we expect them. So this is one of the reasons why we have to look deeper than R value. So as another, the really simple visual way to put it is if we wrap our buildings in continuous exterior insulation, that is both the right density and the right amount of vapor permeability, then we can have safe, durable, high performance construction that stores carbon up front. So with those things in mind, we chose on a recent development that you saw the interior side of with the wool exposed to the interior environment, we have most of the performance of this building relying on our continuous exterior wood fiber insulation. From an R value standpoint, one would have predicted that we needed probably 4 inches of exterior insulation. That's what this building originally was modeled with 4 inches of exterior foam insulation. But we switched to 1.5 inches of wood fiber insulation, and the real world performance of this building is better than had been expected with the 4-inch exterior insulation. That's probably a little confusing, but the point is a smaller amount of wood fiber insulation, a smaller amount of insulation that's like engineered by nature for our climate and the way it works, created better real world performance than R value would indicate. So why does that happen, right? This is a chart showing on the top outdoor temperature swing, and then a chart on the bottom showing the indoor temperature swing related to that, right? And what happens is there becomes a huge time lag when you have high specific heat capacity, high density insulation like wood fiber insulation. Um, the outdoor temperature doesn't change that material itself very quickly, so it creates a buffering effect that's more significant than it is with low density materials, right? The low density materials heat up quicker. The wood materials take a long time to heat up. I'm getting into a lot more technical detail than I normally do on these things, but I figure with a passive house audience, this is what you guys are here for. So here's a little backyard experiment I did just to, prove this out. I built two different boxes. One of them is 2 inches of XPS insulation, so would be rated at R10, and the other is 1.5 inches of wood fiber insulation that's rated at R5.7. So let's say the wood box is R6, the foam box is R10, right? And then I put little sensor push monitors in there, put them out in my backyard in Tucson, and let them sit there for a year. This is a week of the more interesting data that I'm showing you on the right. And the wood fiber box swung roughly within the temperatures of those days. It was getting down to the low 50s at night and getting up to about 90 during the day in that week. So yeah, this box basically adapted to the local environment. The foam box at, significantly more R value had a much higher swing of temperature within the box itself. So the insulation itself wasn't that working that well. And if you look at the humidity distribution, it kind of sneaks in at the bottom there. It's pretty wild. The wood fiber box obviously was breathing well enough to not have a huge amount of vapor pressure build up, whereas the vapor closed box was having enough vapor pressure building up that could cause some issues if this was an actual building, right? So the punchline of this is that in this little backyard experiment, the data, supported the various hypotheses and theories out there about thermal diffusivity in that wood fiber outperformed XPS by a factor of about 2 when it was at roughly half the R value. So maybe 3 times better performance than would be anticipated based on the rated R value. So definitely something to consider if, especially with project budgets getting tighter and tighter, right? If your model's saying 4 inches of wood insulation versus 4 inches of foam insulation, there's no way the client is likely to pay for that additional cost. But if it's 1.5 inches of wood fiber insulation versus 4 inches of foam insulation, those prices are a lot closer and that decision's a lot easier, right? So it's really important to pay attention to these things. And I'm not really sure how, I mean, Passive House does value these things a bit in the modeling, but that's a step of further refinement that I'd love to see. I'm not exactly sure how to make it happen, but love to have those conversations. Um, Another really important thing to think about is that all carbon counts throughout the project, right? We spend a lot of time thinking about operational carbon and Passive House, the energy efficiency that's being delivered, which is wonderful. Every project should be a Passive House if possible, right? Like if we can get to that level of performance, fantastic. But efficiency is a relatively small part of the carbon impact picture that matters in the next 10 to 20 years. In a lot of places. In some places, efficiency still is the number one thing, but in a lot of places, it is no longer the number one determinant of carbon impact. Excuse me while I take a sip there. So the step one in this counting all carbon is calculating for our local reality. So we talk about carbon in this proxy of kilowatt hours or BTUs often, and we need to be doing the unit conversion of kilowatt hours to actual pounds of carbon by understanding how many pounds of CO2 exist per kilowatt hour on your grid, right? So you can find these things in power mix reports from utilities. I used to crunch all these numbers when I worked in the consulting world in Seattle. And in Seattle, when I was working up there, we'd worked really hard to get the grid, down to almost zero carbon, which is fantastic. But it does mean that the energy efficiency in Seattle doesn't have a lot of reduced carbon impact that comes with it. Yes, we have a limited amount of renewable energy and you have to share that amongst a growing population, all these other things, of course. But when you're looking at the payback periods of upfront carbon to how much carbon's actually saved by energy efficiency, even to the extreme of Passive House, there's a lot of scenarios where the payback periods are 50, 100 years, right? To pay back the material cost of having the embodied carbon of all the materials needed to build a high performance building, unless those materials are carbon neutral or carbon storing. If they're high carbon impact materials like foam or mineral wool or fiberglass or whatever, it takes a while to pay back the carbon built into those materials when there's almost no carbon impact on the grid. In Tucson, I was shocked to find that Tucson has about 15 times more carbon in pounds of CO2 per kilowatt hour on its grid than Seattle does. So efficiency means a tremendous amount in Tucson, but we still, even then, need to be very careful about what materials we use to deliver efficiency. That's a really critical thing. So, borrowing this from my buddies at New Frameworks, this is just the simplest, I think, diagram I've seen of a carbon life cycle of buildings. So I really like this. When we're talking about upfront carbon, we're usually talking about material carbon emissions, which in the life cycle analysis standpoint is A1 through A3 of the analysis. And that's raw material extraction and processing and the manufacturing of building materials, right? Another thing we need to control more as project teams is transportation to construction site and the installation energy and carbon impact of installing materials. Been working with a cool project in Bend, Oregon. It's living building net zero to try to figure out how to do this more efficiently, right? We've been putting together a great spreadsheet to track all these things and include the installation and transportation phase into the analysis in a more complete manner. And then another reason durability is mission critical is there's a huge amount of carbon impact when buildings get demolished or taken apart or hopefully, deconstructed for reuse. But we need to make buildings last as long as we can. I think we're all in the 100+ years of durability, if not 300+ years of durability type philosophy in the work we do. So just pointing out that when energy efficiency matters, when operational carbon impact matters, it is a really pretty small part of the overall of the carbon life cycle of a building. Again, not to say it's not important. We should make every building as efficient as we can, but we need to consider how we deliver that efficiency a little more carefully, I think. Another way to say that is materials matter, right? This is an analysis I'm borrowing from my buddy Chris Magwood, who I've been honored to work with on all kinds of cool projects. This is looking at the same building, same performance. I think it's, if I remember correctly, a 20-unit multifamily built to passive house standards. And the only thing that changes is what materials are used to create the building, right? So in the high carbon impact materials, it's a pretty massive upfront carbon impact. In the absolute best practice materials, which a lot of would be very difficult to get or have go through permitting, et cetera, obviously a huge amount of potential carbon storage. So we can aspire to that. But what's most interesting to me is this best conventional, the UEC is upfront embodied carbon. So the best conventional upfront embodied carbon, these are all materials that are readily available that we could put into projects tomorrow. And if you put those together along with passive house, then we get pretty deep net carbon storing emissions over the next couple decades. And that's the exact kind of formula we need to make a real difference right now, right? Is get to the highest level of efficiency, but get there through low carbon impact or carbon storing products. So Rocky Mountain Institute, we were honored, did an article, white paper, whatever, on or included us in a white paper that they did on the hidden climate impact of residential construction. This was our last project called Valley Muse. It's a 4-unit missing middle development that was intended to be built to passive house standards, and living building challenge materials pedal was heavily considered throughout that. So those were the things that inspired that work. And minimizing our upfront carbon impact was a huge part of that too, right? So we got featured in this as like a multifamily project that achieved that. The average number they came to was 184 kilograms of CO2 equivalent per meter squared, right? That's the average carbon impact of residential construction in North America. Obviously, there's a big plus or minus on that, but it's a valuable baseline to understand, right? So 184 is baseline based, from 921 modeled homes, right? That's where that data comes from. When we ran our project through the same modeling, we were really happy to see we'd gotten all the way down to 59 kilograms of CO2 equivalent per meter squared. We were hoping to be at 0 or below 0, but it wasn't realistic for this project for many reasons. But we were really glad to see that degree of reduction. And more than anything, just how easy it was to determine this information in this day and age it's just something that every project should really be looking at, right? So breaking this down a little bit, because I know we all like technical stuff. Our footings and slabs, I just want to point out concrete's what we're always talking about is super high carbon impact and very problematic. We agree. We should definitely create lower carbon concrete and use less of it. But footings and slabs are kind of a set thing we are going to have to work with. So then the question became, what insulation are we going to use? Are we going to wrap our foundation walls with XPS to maximize the R value? Or are we going to take, R4 per inch instead of R5 per inch with EPS and wrap it with EPS, right? Like if you were just looking at efficiency, you'd probably choose the higher R value option. But if you're looking at life cycle carbon impact, it becomes very obvious you should choose the lower carbon upfront option for the slightly lower R value. And then, so this analysis I'm showing right now is modeling out if we had done this Valley Muse project with typical high performance materials that we see in Phoenix all of the time, right? So we see XPS all the time, we see spray foam all the time. So that's what these buildings would have typically been delivered with had we not specified good materials. So this is getting an idea what the baseline impact would have been, right? And so with closed cell spray foam, XPS being the material selected, it ends up at 447, which is obviously a lot higher than the 184 average, right? This ends up being an extremely high carbon impact building, even though it would be built to passive house standards, right? The upfront carbon is just tremendous. So another way to look at this is concrete, and this would have been foam insulation. So the foam insulation would have been about 10 times the impact of the concrete. And concrete's what we all accept is like big carbon impact, let's minimize it, et cetera, et cetera. But I think it blows a lot of people's minds when they see this and realize that foam insulation could be 10 times the carbon impact of concrete. So this is what the Valley Muse project looked like with good insulation, right? Still had the concrete impact, but in this case, we used a recycled EPS that we were able to source. We did our exterior wall systems I showed you in earlier slides with wood fiber on the outside and wool on the inside. And then we did blown cellulose to get the increased thermal mass for the thermal diffusivity reasons. We did cellulose in the roof system, and that brought us down to 59 kilograms of CO2 equivalent per meter squared. So more or less same performance, but dramatically reduced upfront carbon impact, right? And with the timeline, the urgency we have, we really need to be starting from the lowest carbon impact of a building as we can, so the efficiency matters quicker and gets deeper into carbon savings, right? So with the good insulation approach, concrete's now 65% of the total impact. So yes, concrete is still important to address, but we were able to take it from, a minor thing to like by far the leading carbon impact by using good insulation materials. And in the end, that creates an 87% lower, sorry, not less, upfront embodied carbon than Phoenix style high performance. And that puts us 68% below that RMI average of 184. So we're really proud of that. And it was not extremely complicated to use good insulation materials. And those have been the things that, potential buyers and renters have been by far the most excited about is the healthy natural insulation. So one of those reasons that people get excited about these things is in parallel with embodied carbon, we think about limiting embodied injustice. And just as there's life cycles of carbon impact built into a product, there's also lifestyles of potential structural violence against people built into a product, right? So can we limit the harm to people created by the products that we use? Not the harm necessarily on site installing it, but the harm that was caused to create the product in the first place. So one of the biggest problems I think we face in our industry is spray foam, obviously, is from if you've ever heard me talk before. But it's the fact of who we let do the spray foam, right? So often I'll hear some version of this. That work sucks. Let's let the less privileged fill in the blank people do it, right? Like we'll draw something on a plan set and then not really think about how that translates to the whole life cycle of a product getting to a job site and the people who have to actually then install it on the job site, oftentimes without proper training or protection or whatever, right? And it affects people that don't have much ability to protect themselves from those effects. So it's something we really could work on and think about more, I think. I like to explain this as a tale of two insulation approaches. So there's the worst of times, this is best of times, worst of times, right? Which is synthetic. That's foam, mineral wool, fiberglass, etc. These typically require ripping apart the natural world that leads to suffering through displacement of, humans and animals and economic hardship, obviously. Workers in factories, manufacturing facilities are exposed to toxicity, poor working conditions, typically low wages. And then occupants ultimately end up suffering with mold, moisture failures, sick building syndrome from, toxins being released, VOCs, whatever it might be. These materials aren't really great for anyone other than the companies that sell them. And then there's the best of times. There's the natural materials. And this is what so much of our work is about, is this marriage of natural materials with high performance building, right? Like bringing these two things together. And that's wood fiber, that's cork, that's wool. We've been really excited to get involved with more projects that have straw and rammed earth and these kind of things, right? Like it's going back to that thing about creating joy through construction. Natural materials create joy throughout their whole product life cycle, right? It really is cool to see it happen. And that's because they're produced in harmony with nature. They sustain environments, they improve lives. The workers typically have much healthier working environments, way better paying jobs. The occupants that live with natural materials then have healthier, more durable, and more comfortable spaces. So for me, insulation's often thought of as this just like after the fact choice. I know not in the passive house world, but it, for me, there's almost nothing more important than what insulation you're using. It's one of the highest volume things you use in the building. Like it really does matter. Um, a visual way to summarize this with a quote is life cycles of harm cannot be solved by a performance standard. Way too much stuff has happened before the performance standard can make a difference, before energy efficiency starts mattering in the sense of passive house. So we need to be as cautious as we are about modeling our thermal bridging of a window or whatever, right? Let's take that same degree of caution in looking into the life cycles of the products that we use so we don't harm people in our planet. Alternatives, these are, healthy jobs. I should have probably been wearing a mask. You don't want to breathe wood dust even. But point is, like, this is basically full protection you need for this insulation. And that comes from sustainable forests, in this case from the Black Forest in Germany. And we've been using it on residential projects, on commercial projects, like you see on the right side there. This is at the Desert Botanical Gardens in Phoenix. Awesome project. Happy to share more details about. We're going to be writing some blogs and doing some videos about that. You can find in our open source online information. But it's hard to emphasize enough how much, I guess, more enjoyable it makes projects when you're using good materials. People get more engaged, I think is a good way to put it. So then building for good. Obviously, we mean this in the sense of positivity and having fun doing it and those kind of things, but also we mean lasting for a really long time. Build so buildings last a really long time. In general, passive houses excel at that, right? But there's two things that we often see people missing on projects around fire and around water management. And I just want to wrap up what I'm talking about tonight by stressing these two things a little bit, and then we can get into questions and whatnot. So build for good. The first I'm going to dive into here is building to resist a fiery future, right? Tragically, we see more and more fire events. From the wildfire smoke to houses actually burning down, it's obviously not been ideal. Going back to core principles, one of the things I want to stress about this is that air moves from hot to cold. And just as moisture can, catch a ride on air leakage and cause convective moisture transfer, where the water vapors catching a ride on the air leakage, embers from fire can be pulled along with air leakage into buildings that's occurring because it's way hotter outside than inside. So little visual demonstration of this. Um, leaky cabin gets super hot when it's a hot day outside and the heat's going in from hot to cold, right? That's the first passive house built. If you probably recognize that being this audience. And I'm a Lord of the Rings fan, so I used Gandalf to say, "You shall not pass," right? Like the air leakage doesn't move into there, so the heat doesn't move in as quick. During a wildfire event, it's kind of a similar idea, but you have even more hyperheated air. Air might be like, 300 degrees instead of 105 degrees or something. And that same air leakage pathway that brought heat in can bring embers in and then cause a fire. Whereas in passive house scenarios, that increased degree of air tightness, when it's properly protected, can limit the risk of fire because it limits the amount of heat transferred into the building, right? So as a tragic and also cool and interesting example of this, this is a passive house project I worked on back in the day in California, with my buddies at Carmel Building and Design. So these photos are from them. This is the inside of it. You can see a little wall mock-up. It's wood fiber insulation on the inside. It's dense packed cellulose on the inside. And this is being built in a very high fire risk zone. So a little further along in construction, a fire came through that area and burned down the entire neighborhood. This is the really tragic element of it. The interesting element of it is this is the passive house after the fire, right? They had proper site protection. They didn't have a bunch of, old logs against the house or anything. So that obviously helped a lot. But one of the things that allowed it to work is there was a durable air barrier that was protected by a high thermal mass insulation. So it limited the amount of heat that gets transferred to the air barrier itself. And then that high thermal mass insulation is protected by ember-proof cladding and roofing, which means that the embers aren't going to get pulled into the ventilation channels and cause issues. So this magic formula created an extreme degree of fire resistance. And the point of it was to do a low carbon passive house, but it ended up being an extremely fire resistant building as well. I was raised by a dad who is an energy efficiency professional who is a bit of a hippie, and flow like water has been a saying throughout my whole life. So I like to call this building to flow with water. Obviously, in this crew, you guys recognize ventilation battens. In this case, these ones are interesting because they're 2x4s, because this was over a 20-foot tall span, and we needed a deeper ventilation channel to make sure there wasn't a bunch of turbulence that built up and prevented ventilation air from flowing through this ventilation channel. And you can see they curve over the top with a bug screen, so that the vents on the other side of the parapet. So it's a hidden exhaust, but it fully wraps with all of the ventilation battens. So this was one of the things we do to help make sure our assembly's dry, because we were putting a 3-coat stucco over this and did not want it to be cracking with vapor pressure. Um, so the magic formula is drying has to be greater than expected wetting. This is a formula I've used for a very long time. It's kind of the basis of design, if a lot of what we do for enclosure systems. And the fundamental premise is that we can't prevent things from getting wet. Everything is going to get wet at some point somehow. So we do have to make sure to think about how that system's going to dry as well as possible within our climate zone. We need to also think about how to minimize wetting, but the really important part is to make sure the drying is greater than the wetting, not to assume we can prevent an assembly from getting wet. That's almost impossible. So add to that do not use list that we have most vapor closed materials, with the caveat of, other than for low pitch roofs and flat sills and other things where they're pretty darn necessary, most vapor closed materials should be on a do not use list. Proceed with extreme caution with vapor closed materials is the main point. And this matters more and more in passive house than it does in typical building, because, as I like to say, all leaks are not created equal. Longer, slower air leakage pathways leave behind more moisture than big leaks. A way to demonstrate this is a cold window. You blow really hard on a cold window, it doesn't really fog up. You blow softly on a cold window, it fogs up a ton, right? So in passive house, we're taking what has been historically a moisture failure highway and turning it into a moisture failure tightrope, in the sense that more wetting will occur in a passive house because we have the air leakage that does occur is in longer pathways typically and moves slower. So we might get increased wetting. And then there's a really good thermal envelope. So we're going to have less drying because there's less heat flow through that by definition, right? So passive houses can be the most durable structures for sure, but you do have to make sure to proceed with extra caution in terms of how you manage moisture. Last point I'll make on this is that performance occurs at a microscopic scale, right? we think of things as macroscopic, like, oh, Tyvek looks so similar to this non-microporous membrane, like, I don't know, Mental 1000 with Procleamer or whatever, a Sega product, right? Like there are people are just comparing what they look like on the surface, not looking at the chemistry behind them and how a microporous membrane is coated in PFAS chemicals, which are those forever chemicals we're all now scared of that are building up in all of our bloodstreams and all the animals on the planet and all that. Microporous membranes are coated in these so that water, piles up and runs off the membrane because it just has a bunch of little holes in it to try to breathe versus non-microporous membranes, which have no chemical coating and breathe in a very different way, right? One of them requires toxicity along with it, the other one does not. So this is also worth pointing out that the microporous membranes don't really work as well as the non-microporous membranes in the sense that those little pores are literally just physical little holes. They're microporous, right? They're punched holes. And if too much water vapor is trying to get through at the same time, it's like a crowd trying to leave a stadium, like the exits get backed up. And when that happens, the water condenses and you can get condensation even on something that has a relatively high perm rate because that perm rate was determined in a laboratory test versus what could occur in the real world in terms of moisture loading, right? So we need to be very careful about the microchemistry of the products that we're specifying for air and water protection and understand that permeability as a rating is useful, but we need to ask more questions about how is it permeable, what chemicals are required to make that happen, et cetera, et cetera. So our magical formula, as I keep saying, is this was my best attempt to break it down into three simple things, which is curate good ingredients, design for comfort, efficiency. If you can guarantee comfort in a building, it is guaranteed to be a hyper efficient building, right? So efficiency doesn't engage people often as much as comfort does. So we often say we design for health or we design for comfort, and efficiency is the side effect, just in terms of how we talk about it to clients. And then build with love, just like we need to cook meals with love. We really do need to approach the work that we do with appreciation and excitement. So, quick example of our work. This is that Valley Muse project. This is a rendering of it from the outside. Ended up looking almost exactly like this when it was built. And we'll go explore one little element of it. So it had this shared driveway to create a social place, achieve that missing middle element of community connection. And then each unit has its own little private walkway that goes down it. And that arrow points down there, and that's what the walkway looks like. You're walking on a little dirt path with like a fountain and greenery now. And there's a little upper deck that comes out of the upstairs living room, which is there. So standing on that deck, this is showing red list free performance layer called Solitex Adhero that we used as a self-adhered membrane. This was our primary air tightness and water control system. Then we covered that in the 1.5 inch of wood fiber insulation. And you can see that white stuff around the windows. We used a liquid applied material called Viscon to make sure the higher risk elements of where the wood fiber interfaced with fenestrations, top plates, base plates, those kind of things were detailed to minimize the risk of wicking through the wood fiber and just help, thinking about this from a 200-year perspective. That's why we added those details. And then you see those ventilation battens. And then we finished it with a Koya and a 3-coat lime plaster finish, which just dramatically lower carbon impact than synthetic plaster. And the Koya is a very low carbon impact material too. The windows are framed out with black Koya on both sides to cover up the tapes we use to make them passive house level of air tightness. And then we can take a little look at the living room. And one of the things I'll point out is this slat wall, which was designed for interior acoustics. This is material that's often used in music studios and recording studios. And since passive houses are really quiet because they have hyper insulated walls, one of the other things we suggest and have found very important to pay attention to is the interior acoustical elements of them, right? We hear things a lot better when it's really quiet, when we're isolated. We don't want things to be entirely quiet. and we want to be able to pick what noises we hear and make sure like conversations don't echo and all these things. So we put a lot of thought into acoustical comfort and how we do our interior sound walls, all those other things. Um, Showing again what's behind these walls. There's the blown wool insulation, and then there's wool bats, I believe, or maybe that's blown. I think that's the blown as well, behind this wall. And that's I guess like a cutout, if you will, of the felt with the wood slats over it. That is for the sound management. And as I had alluded to earlier, we left the wool open to the interior environment, as in vapor permeable drywall over it, or this vapor permeable felt over it, to help modulate humidity levels inside the building. And the results are pretty cool, right? This is what Muse looks like versus my house in the same time period, right? There were some, air quality spikes, probably someone burnt toast or something, where it goes down to 59 on the top chart. But the overall daily average is 94 air quality versus 74.2. And I hope you're asking this already yourself. How is it, of these five things it's measuring for this aware score that I'm showing here, temperature, humidity, CO2, chemicals, PM 2.5, how is humidity influencing these things? Like, is the wool actually working? And we think so. The humidity stays pretty modulated throughout a very dry period of time, where in my house, the average is below 30% and gets as low as below 20% inside, which is probably why my voice sounds like it does and why I keep drinking all this water, because the humidity here is like crazy low. Um, I wish I could be presenting from a building that had like 42% daily average humidity. And the natural materials certainly help with that kind of thing too. So not only do they help solve all these problems with life cycles of injustice and carbon impact and all these other things, but they also actually help our buildings perform a little bit better and tell better stories and get people more excited about them. So I guess the fundamental message really is, make sure you use natural insulation whenever you can, instead of synthetic insulation. And with everything else you're doing, make that simple change. And honestly, I think you can just level up your work pretty simply. And if you're already doing that, then hell yeah. Thank you so much for doing that. Um, I'll wrap up by saying, I was trying to explain this to my kids and I said this to them. So buildings are what they're made of, just like you are what you eat, right? Like from an ingredients first mentality, we can think about that. There's been so many times I've been in rooms with people who only eat organic food, who only wear wool clothing, who are talking about spray foaming the room they're sitting in. And that breakdown of logic is a lot to me. So we need to apply that logic we often apply to the food we eat to the buildings we live in. And again, I'm Lucas Johnson. I'm the chief building nerd with Nopal. And this is my fun way of saying this is my business partner's older kid when he was a baby being offered veggies he didn't want to eat. But this is how I want you to react when someone suggests synthetic insulation. Just at least skeptical. Maybe if you have to use it, all right. But at least ask some more questions about it and look at it from a deeper perspective than our value and whatnot. And now I will wrap it up and open it up for any questions.
This is fantastic, Lucas. Wow, it's one of those Socrates uh, presentations. All I know is that I know nothing after listening to this. It's really great. Thank you. Thank you. Yeah, there are some questions on the chat. Do you want me to read it or can you read it?
Let's see on the chat window here.
Yeah.
Yeah, I think I can pull that up here. All right. Oh, you had asked about the devices we use to measure and log data.
Yeah.
Yeah. So the thing that you saw on the last slide there, that's
Mhm.
from an Aware device, which is one we often give out to clients. It's, a plug and play thing. It works with an app on the phone. It's pretty darn accurate, right? The sensors can't really be repaired and tuned like higher end devices could. So if you're doing like university grade research, you want to use a better system than this. But if it's tracking what's happening in a client's house. Like these are great devices to do that inexpensively.
And what's the brand name?
Aware, like
Aware.
AWAIR.
Great.
Yeah. And then the little things that I put in those boxes that I was measuring, the wood fiber versus XPS boxes, those are called sensor push. And those are just little sensors you can put somewhere. You can like leave them in a wall. You can, put them out to measure, humidity. Like you want to make sure your fridge is storing food well. You can throw it in the fridge. They're just like little, and then they eventually run out of batteries and you throw them away. So the life cycle design of them is not that great, but sensor push is another inexpensive thing. You can buy it on Amazon. They're like $60 each.
Got it.
But to be clear, sensor push is just uh its temperature, humidity. That's it. Whereas
Okay.
Aware does PM 2.5, chemicals, temperature, humidity, and CO2.
And have you done something like having a sensor outside of the building and one sensor inside of the building and comparing?
For sure. We
Mhm.
so my undergrad was in physicochemical biology, and I worked with this group called the Center for Embedded Network Sensing at UCLA, and it was all about monitoring ecological systems. And basically, ever since then, I've been trying to figure out how to rebuild that in buildings.
Mm.
The challenge is it's like at least 10 grand, if not 50 grand to do
Yeah,
something like that for a building. So unless a university is sponsoring it, I haven't had a client yet to pony up and, you know, pay that 50 grand extra or whatever to do it. That being said, we keep, the team I work with now, with Nopal, like this is the stuff we talk about all the time. One of our biggest bones to pick with building science is every building's a hypothesis, yet we don't collect data, right, about the buildings we build because it's too expensive to do. So it's like not really science in that sense. Like we're not actually verifying our hypotheses directly through measurement in a sufficient way. So we would love to see measuring building performance become less expensive and something that everyone does.
I see. Anyone else a question for Lucas?
Yeah, I have a question. Thank you, Lucas. This was an incredibly insightful and well put together presentation. I appreciated the kilograms of carbon dioxide equivalent per meter squared saved that you talked about for the Muse homes. I was wondering if you've calculated out the cost per kilogram per square foot saved, the
Ooh,
incremental cost.
ooh, no, that's really interesting.
Hmm.
So yeah, and that data would be so difficult. Part of the reason we didn't is we ended up building Muse in the middle of the pandemic, and timelines, prices, et cetera, were just all over the place. I don't know if there's really meaningful data to be gleaned from that.
Hmm.
Um, Experientially, from working on a lot of these projects and seeing a lot of how these prices shake out, um, we're talking about a rounding error. If we're talking about the difference between what I would call bad insulation and what I'd call good insulation, it's a rounding error on the overall budget. I mean, it's less than 1% of the overall budget usually, the cost difference. It's really not huge. If you look at a line item of wool versus fiberglass insulation, that's probably like 3 or 4 times as expensive. But if you look at that as the overall budget of the project and is 1% more worth achieving all these goals we're trying to achieve, that's how we tend to talk about it. And the answer tends to be yes when you talk about it like that.
Okay, thank you. And I have one other question as well. Um, so when I've brought up using wood fiber insulation in particular, even in projects that have ambitious embodied carbon goals, I've received a lot of products, thinking of Gutex here, because of the transportation emissions. And I was wondering if you could talk a little bit about how you think about that in your work.
Totally. Yeah, it's because of the urgency of carbon impact right now and us keep getting closer and closer to a deadline, we do jump forward when we have some degree of accuracy without the precision that would be ideal in general, right? I mean, we did that with energy efficiency until we had Passive House, and now we have something that can provide precise prediction of energy performance, plus or minus about 5% from modeled to real world, right? We're getting there with embodied carbon, but it's still plus or minus quite a bit more, right? So, yeah, it's an ongoing process, but because of this urgency, the easiest part to address was the A1 through A3 emissions, which is the manufacturing and material harvesting and that kind of stuff up until when the product's made, from the harvesting through the product being made. That's pretty easy to standardize, measure, and et cetera, right? Transportation emissions and installation emissions, like we're trying to do this on a project now, and we're having to get the GC to get his plumber and electrician and everyone else to give him like gas receipts and all this other stuff to talk about miles driven and all. And they're willing to roll with it, sort of, right? But getting that data is hard. I put together a great spreadsheet to track the data, but actually getting the data into that spreadsheet is going to be a whole other thing. Um, that being said, tracking product emissions, like I built this spreadsheet that you can say first thing was by ship, second thing's by rail. Here's the standard emissions per mile per pound. How much was this shipment weigh? And come out with like an average of like, I ordered this product from so and so, right? And a ton of other people have looked at this stuff. And when you go to a product like Gutex, when I was still at 475, we took great care and a lot of time and effort to hire people to calculate these things of like, is it still carbon storing by the time it gets to New Jersey port, Portland, right? And on a ship, yes, container ships, the incremental weight of insulation, very little. The carbon impact per mile per pound is very small for something on water, right? What was crazy to find out is the trucking distance matters very quickly, right? So like 300 miles on a truck is basically the same carbon impact as going from Germany to Portland. So that's the part we really need to pay attention to, is the intranational, the shipping within our nation rather than the shipping from one to another. That's very incremental, it turns out.
Along those lines, I wrote on the chat. What do you think about? Yeah, I know it's a phone board, but what do you think about GPS?
GPS is a material we'll use in certain applications on a roof system right now for a client. We're using that very low pitch. We ended up with vapor closed roofing materials anyway. We're not purists about anything, right? I used a lot of spray foam in my career, and in utility programs that I worked for, we encouraged it. Like until I collected enough data on it, I also did that kind of stuff all the time, right? So um, GPS and EPS are like, are you familiar with that idea of like less bad versus good, right? That whole thing, right? Yeah. So we like to think of EPS and GPS as best of less bad,
You bet.
right? And then natural materials are from good to best, right? But
You
that
bet.
gap between best of less bad and worst of good, if you will, that's a pretty big gap often. Um, GPS, interestingly, is sort of carbon impact wise, performance wise, depending on the thickness and the project and the climate, all these things. GPS might be somewhere in between the purgatory between best of less bad and worst of good, right? Like it might be in there because of having some degree of vapor permeability and being relatively low carbon impact. It's EPS and GPS are typically, well, another challenge we have here is we talk about these things in product categories like foam insulation or EPS and then assume all EPS is the same or all GPS is the same. Often they're pretty different, right? So but in a generalized sense, EPS, GPS are 5 to 10 pounds of CO2 maybe per cubic foot. XPS is usually more like 50 to 100. It's massive difference between those. So like XPS and spray foam are up here at like the highest carbon impact per cubic foot for insulations. GPS, EPS, fiberglass, mineral wool, those are all kind of right around here. And then the carbon neutral, carbon storing options are all of the natural ones, and those, yeah. And frankly, those just perform better too. And people like get excited about them. Like we have this bowl of, when we were doing tours at Valley Muse, we had a bowl of sheep wool out on the counter. And people would just be like, wait, the walls are what? No way. And pick up the wool and like rub it on their faces. Like, honestly, what other insulation can you think of that you would rub on your face? Right? So,
That's right. That's right.
anyway.
Well, thank you so much. Is there another question over there? Lucas, this is incredible. This is exactly what we need, especially for our Southwest um, uh, hot, dry, high altitude climate. Someone that understands that most of the materials and products and equipment that we get, the information, it's humid stuff and the different.
I could not agree more. Funny example would be, we use this windowsill tape. I moved from Seattle to Tucson. My wife's a professor and went from UW to U of A. So that's why we did that like 7 years ago. I was using a ton of these Proclima products up in Seattle using a windowsill tape that's black in color, right? Never had a single problem with that up there. We installed that on a building in Phoenix in summer and it basically slow motion boiled off the building. So then we started using this capillary break tape that's now colored white so that it doesn't absorb the UV. So it's a sill tape we can use in our climate. And you're absolutely right. If I ever do a PhD, which I've threatened to do many times, it would basically be on the knowledge transfer of what we know about high performance, but making it work in our climate. Because I
Yes,
love the Southwest, right? Like,
yes.
and I want to see things that work well here. So
That's wonderful. That's so wonderful to hear. And it's very interesting, not only for our unique climate, but also it's a unique culture. It's a unique type of building, the only regional style of architecture in North America that is really from here. It wasn't, it didn't come from somewhere else. So it's
that's a really
really,
good point. And
mhm.
so much of natural building has come from this region, right? So like um this marriage of high performance and natural building. I should give a shout out to my buddy Ray at Natural Building Works, who I've worked on a bunch of projects with. Or the goal is that like trying to bring high performance building and natural materials together, because we often have this thing of natural building versus efficiency or something, right? It's like it's both, right? Like
Absolutely.
uh
Absolutely.
and I'll end with this. I think you'll appreciate this because you've worked in this region. I like to say if green building was a video game, Arizona's the final boss. Right? Like the culture here of just building quickly, and it's either like dirt of the earth, raw, we get it done kind of stuff, or like high-end custom homes that are like basically tract homes built bigger. Like it's been really difficult. Like in Seattle, there's a huge history of like quality carpentry as a whole culture, right? Like it wasn't that hard to get passive house type buildings built, whereas we've found it to be much more challenging here. But you know what? We're enjoying it, and hopefully we can all work together to make a lot more of these good buildings happen.